Today we're going to continue our discussion of a trip through geologic time and talk about relative dating. Relative dating is putting layers of rock in order according from the oldest to the youngest. And this little exercise here is a similar notion where you're looking at what happened, you're using evidence. The footprints in this case are your evidence and you're trying to put things in order. So why don't you take just a moment and pause the video and see if you can tell what happened in this situation in order from the oldest to the most recent thing. So by doing this activity, what you just did was you relatively dated the events. And we're going to do the same thing with layers of rock that we see in lots of different examples. So relative age is just a rock's age compared to the rocks around it. It is not a specific age, and we are not able to give it a certain date of when it formed. The absolute age of a rock is the number of years since the rock formed, but in many cases this is impossible to know. We will talk about absolute dating in the next section. In the late 1600s, a doctor named Nicholas Steno proposed 4 principles about the formation of rock layers that helped explain evidence that we have about the rock layers and helped to relatively date them. Rock layers are also called strata, and stratigraphy is the science of strata. Stratigraphy deals with all the characteristics of layered rocks, and it includes the study of how these rocks relate to time. Steno's first law is the law of superposition, and this is the one that you read about in section 2 and that we talked about in class. This tells us that the bottom layers are the oldest and the top layers are the youngest. So in this picture here, layer G would be the oldest one and layer A would be the youngest. Sedimentary rocks are formed particle by particle and bed by bed, and so the layers end up being piled on top of each other. Thus, in any sequence of layered rocks, a given bed must be older than anything that's on top of it. This law of superposition is fundamental to the interpretation of the history of the Earth, because at any one location it can tell us the relative ages of the rock layers and the fossils that are in them. So please pause this and take a moment to write down the brief description and the picture in your notes. The Grand Canyon are layers of rock that we refer to a lot when we're talking about relative dating, and that's because we see these layers really nicely. You can see the difference in color and texture. And so in this outcrop here, we can see that the Supai group on the bottom is going to be the oldest, and the limestone on the top will be the youngest. Steno's second law that we're going to talk about is the law of original horizontality. This tells us that the rock layers were horizontal when they were first deposited. Layered rocks form when particles settle from water or air. Steno's law of original horizontality states that most sediments, when they were originally formed, were laid down horizontally. However, many layered rocks are no longer horizontal. Because of this law, we know that sedimentary rocks that are not horizontal were either formed in some very special, unique way, which doesn't happen very often, or more often, they actually were moved from their horizontal position by some events that later happen, such as tilting, when mountains are built, and that sort of thing. So in this picture that we see here, this is how they were originally layered. So D is the oldest and A is the youngest, but through some event that happened in history, they ended up being tilted like we see at the bottom here. And more often, we see tilted layers more often than these horizontal layers. So take a moment to write down this brief description and the picture. Next we have the law of lateral continuity. This says that sediments were deposited in continuous layers. So when we have a valley, like you see below, that cuts through the sedimentary layers, we can assume that the rocks on either side were originally continuous. So we can assume that layer A on the left and layer A on the right were one formation at one time and since have been cut through, like you see below. Our last law is the law of cross-cutting relationships, and this tells us that a rock formation or any sort of surface that cuts across other rock layers is younger than the one that it disturbs. So here's a common example we see. This is an igneous intrusion, and so these layers here are sedimentary rock, and this intrusion is igneous, which means that magma penetrated these layers and then hardened. So we know that this intrusion happened after all of these layers were deposited. We apply this law to things like faults, which are a break in the Earth's crust. A fault is always younger than the rock that it cuts through. So in this picture that we see below, the fault that's labeled by E happened after A, B, C, and D were already there. And we can tell that because they're all offset by the fault. So the fault E is the youngest thing there. And then like I mentioned in the slide before, we also see these intrusions, and if they're on the surface, we call them extrusions. And these are almost always igneous rocks, and this is where lava penetrates and then hardens. So in this case here, we see intrusion D that happened, and we know that that happened after A, B, and C were already there because it cuts through those layers. And we can also tell it even happened after it's younger than the surface as well. So if we were to put these in order from oldest to youngest, we would know that C happened first, it's the oldest, and then B, and then A, and then intrusion D, and then fault E was the last thing that happened because it cuts through all of the other layers. Unconformities are another thing that tell us about the history of a rock formation. And this is where we have rock layers that have been lost due to erosion. And they represent some sort of time gap in the geologic record. So as we see in the picture here, in number 1, we see all of these different layers that were originally deposited horizontally and then compressed and formed mountains. Well, then what happened is that those layers eroded away by wind or rain or water, and so we're left with what we see on number 2 here. After that, other layers were deposited on top, and we can see there's some sort of water or ocean on top of that. So if we look at 3, we can tell that we have some missing time here, because obviously these layers were at once continuous and have been eroded away, and then we had layers put on top. So this represents some sort of missing time. We see a lot of these unconformities in the Grand Canyon, and you can see them all labeled here and shown with the red line, and those represent some erosion that happened and some missing time. So I want you to take a moment and do this little exercise and just write down on a scrap piece of paper what you think the order is of these different layers, and if you think there's an unconformity and when that happened. And pause the video while you do that, and then I'll give you the answer in just a minute. Okay, so hopefully you have written down what you think the order is. And the oldest event would be number 5, the schist, and then the sandstone in number 4, the limestone number 3, and the shale number 2. Then we have number 6, this basalt intrusion here. And then it looks to me like there was some erosion happening. So here's that unconformity right there. And then lastly, we have the conglomerate on top. So the conglomerate will be the youngest. Here's another quick activity for you to do. So again, pause the video and see if you can come up with the order. So the correct answer is layer T is the oldest, then layer A, then the intrusion, because it passes through both of those layers, and then the fault, and then layer K, and then some erosion. And we can tell that layer K happened after the fault because we don't see a layer K on the right-hand side. And that should be below here if it happened after the fault, or sorry, before the fault. Fossil correlations are something that we can use to correlate the ages of rock in one area to the ages of rock in another area. Rock layers are dated by assigning a relative age to a layer of rock at one location. The same age can be given to matching layers at another location if they have the same index fossils present. These help geologists to match the rock layers, but index fossils have to meet 2 criteria. They have to be widely distributed across the world, and they also have to have lived for a geologically short time. Index fossils tell us the relative ages of the rocks where they are found. We don't use index fossils to relatively date the layers of rocks in one area. This is just for correlating rocks in one area of the world to rocks in another area. So for example, in this picture here, we have rocks from 2 different locations. And what we can tell is if we match up some of these index fossils, we can tell that layer 3 on the left and layer 3 on the right happened around the same amount of time because they have the same index fossil. The same can be said for 4 and 4 and 6 and 6. So if we were to put these in order, we use the law of superposition to say that 1 is the oldest, and then 2, and then 3 on both sides happen at the same time, 4 happen at the same time, and then on the right here we have 5, which we don't have on the left. So on the left we must have an unconformity and some missing time there. And then layer 6, and then 7, and then 8 would be the youngest. So that's it for our video on relative dating. If you need to review anything, please go back and do so and make sure that your notes are complete.